I'm going to take a shot at the differences that happened when we went from NVMe MI 1.2 and we jumped all the way up to 3. You're like, why did they jump so far? And you're going to see there's quite a bit of change in the first 3 topics here. And there's a lot of cleanup in the next 4 TPs, and then the final one is kind of on a tangent. But all of these TPs were starting to impact each other and overriding each other, and it became quite a nightmare to keep them all healthy together. And there's a lot of change that came with this version, so we made the decision that we'd step all the way up to 2.0 and make that more visible to everybody else. So you can certainly go and read all these TPs and see what the differences were. We're not going to go into that kind of detail here today, but we will cover the problem and solution of the first 3. So the first problem here is that when you had an NVMe system designed before, that the management of the device, the entity, the SSD, was difficult in a dual port solution. In a dual port solution, you have 2 hosts on the top, host A and host B. They each have their own PCIe port connection down to the SSD, and you have that shared namespace at the bottom. If host A was to disappear, for example, there is no easy mechanism for host B to take over the management of that system, because all of the status information was shared between the 2. So if one host was reading the status and there's a status event that changed and then it cleared it, the other host wouldn't know that the first host had cleared it. So a lot of these mechanisms had to be improved. The second problem is that there's only one SM bus port, and you can see kind of the green lines go around the bottom. There's an SM bus port coming in from the bottom, and there's no way to share that SM bus port between the 2 different hosts. So companies have done their own thing, but we tried to come up with some solution here for the work group, and we'll show that on this page. We took 2-pronged approach. One approach was we went to DMTF, that's another standards organization, worked with them to come up with a way to send, or they had a mechanism already. They treated the drive as a non-bridge device. So if by using their bridge mechanisms they had already defined, we could add more than one MCTP endpoint to a management port. So you can now come in and you can say, hey, management endpoint 1 is going to be host A, and it's going to have its own set of status information. Management endpoint 2 will be for host B, and it will have its own set. So they don't collide with each other anymore. And likewise, host A and host B, sometimes people don't use SM bus for this. They might use the in-band tunneling mechanism. All of these mechanisms are duplicated so that host A and host B can be independent. All right, the next issue was for polling the device. So when you have a bunch of these drives, say that you got 24 of them or even 32 of them in your array, and you have to go check each drive, the mechanism that was used today typically is to have an SM bus mux, and it switches this drive on, it connects it to the BMC, it does communications, it's checking what's going on, then it switches over to the next one, and it does communications over there, and it goes to the next one. It has to get through all 32 of those and back to the first one before the fan speed gets too far behind. And so let's say that they want to have the fan speed updated every 5 seconds. It has to go through all of the drives and get back to the first one in 5 seconds and update the new fan speed. So I'm just using fan speed as an example. There's several other different events that we've added here for other than temperature. But what you can see is on the left side is this idea of a AE disarmed state. This is before you turn on event reporting. Then you have the armed state. During this state, it's collecting events. So you could have more than one event happen. You see the first, there's event 2 and was it 3 and 4. Those events happen during that state, and they get kind of grouped together. So you only send one event back to the host for those 2 that happened. And it's probably kind of small there for you guys to see. But the next green, but the one right before that group there, that's the one where you're sending the what do we call it? They had a name for it here. The coalesced group of events back to the host. And then we have some examples there where if the event notification fails for whatever reason, doesn't get through, there's a mechanism to detect that we don't get a sync with the host. And then there's a retry, and if another event comes in during that time, there's a lot of details and stuff in there that you can go read the TP, and you can see all the corner cases were well covered. And that solution should now make it so that when you use something other than SM bus, so you have to use either I3C or PCI VDM, and you can have this connection to all the SSDs at the same time, and whoever is alive and has an event that happens can send that event back to the host or the BMC, depending which management model you're using, and it can then act on that, and it can do something much faster. And the third thing I was going to show is NVMe. So let's go back a little bit. PCI SIG came out with the mapping. Well, a lot of specs worked together to increase the speed of SM bus from I2C speeds to I3C speeds. And I3C is much faster, and so we looked at it from NVMe group, and how can we give that benefit to our storage users, like our customers up here on the table, and help them to be able to manage their SSDs much faster. Two problems that we had were that if you're doing a firmware update over this out-of-band interface, it could take minutes, multiple minutes, or even more, depending how fast your interaction is going on. But there's a lot of data to transfer at 100 kilohertz or maybe 400 kilohertz. And so we can now go from minutes down to seconds with I3C. The other thing is that the SM bus architecture only connects one SSD at a time, typically, to the endpoint. So say that you've got those 32 or 24 SSDs I talked about before. Only one of them will be connected to the BMC. It'll talk to it. Then it will switch the MUX over to another one. It'll talk to that one. And so, like I said before, that caused problems from the event reporting perspective. You can't do event reporting. It also causes problems from a latency perspective. So say that you want to send out some work to a whole bunch of SSDs. You got to do the work on one SSD, then the work on the next SSD. So you serialize all that work. By going to I3C, there's an I3C hub that Intel defined. It's this picture on the right, that pinkish background blob. It has 2 ports to the upstream side and 8 downstream ports. And this is an open spec. Renesas and TI make this part. You can buy it off the shelf. And what it does is it lets all the I3C traffic flow through. And any of those devices on the backside can say, hey, I'm ready to start sending something back. And it's just transparent so that both the BMC and the SSD don't need to know how many devices there are. They just say, I have a message to send, and the I3C hardware takes over. So what this does for our manageability solution is it gives us a well-defined environment. PCI SIG, MIPI, DMTF, and all these other industry specs have come together and defined how this works together. It's an order of magnitude, at least an order of magnitude faster than SM bus is today. And it enables the BMC to control the clock for all of these devices. So the problem we had before is that if you didn't have that SM bus MUX that switched just to this SSD and into that one, is that this SSD could actually send traffic to the neighboring SSD and pretend that it's the host. And thus you could get undesirable things happening on your backplane. With I3C, that changes because now the BMC always controls the clock, and nobody else can make any traffic flow unless the BMC clocks it through. So that everybody controls their data pin, and the host controls the clock pin. And there's new tricks that they had to come up with to make that work with I3C, where you can you send any kind of an IPI, they call it. It's an interrupt to say, hey, host, I need attention. Once the host gives you attention, then you can clock out your data with the host clock. And so what the advantage of this in the end here is that you get faster data transfers, and that you can interleave all this traffic. All these SSDs can get whatever command you want. Say that you want to send a security erase. You can send a security erase to everybody at the same time, and whoever's done first will just send their event back to you that they're done. And so you don't need to do all the work on one SSD first and then the next one. That's all I had.